Welcome to This Explainer. Today, we're literally going to dismantle your everyday intuition about motion. If you think you've got a solid handle on exactly why things move the way they do, well, get ready, because we are about to entirely shift your perspective.
All right, let's jump right in with a surprisingly tricky question. Imagine a kid pulling a toy car on a string. They have to constantly drag it to keep it going, right? So what actually dictates why things move or stop? I mean, it feels incredibly obvious at first glance. You pull the string, it moves. You let go, it stops. Simple as that. Or so it seems.
Now, that perfectly relatable everyday experience actually led the ancient Greek philosopher Aristotle to a very firm conclusion. Our common intuition says, hey, the car stops the second you stop pulling. So Aristotle took that and declared that an external force is always required to keep a body in continuous motion. And you know what? It's a highly logical view. It makes total sense, but it's also entirely flawed, and it actually managed to trick humanity for centuries. See, there's a hidden villain in the scenario that Aristotle completely missed, the ultimate illusionist, really, that tricked the smartest minds on Earth for thousands of years. We're talking about friction. Friction inherently opposes motion. So that kid dragging the toy car, they're actually just applying exactly enough force to cancel out the floor's frictional resistance. That's it, because the mind-bending truth of the universe is that uniform motion actually needs absolute zero net force. It was actually Galileo who cracked this mystery. He did it by imagining a completely frictionless world through this brilliant double-inclined plane thought experiment. Let's walk through his logic really quick. Step 1, imagine a moving ball rolling down one ramp and up another, reaching just about the exact same height it started from. Step 2, if you decrease the slope of that second ramp, well, the ball has to travel a much longer distance to try and reach that original height. And then step 3, this is the absolute genius part. He realized that on a perfectly smooth, flat surface with zero slope, a moving ball would just travel infinitely. It would keep going forever, trying to reach that height without ever stopping. And that beautifully brings us to the core concept of inertia. By definition, it's a body's innate property to resist any change to its state of rest or uniform motion unless it's compelled by an external force. But honestly, simply put, it just means objects are incredibly lazy. They literally just want to keep doing exactly what they're already doing. This fundamentally establishes something crazy. Being completely at rest and moving at a constant uniform velocity are physically equivalent states. Nature literally does not prefer one over the other. Let's move into part 1, the rule of zero, also known as Newton's first law. Building directly on Galileo's profound insights, Isaac Newton stepped up and formulated his first law of motion, stating that if the net external force on a body is zero, its acceleration is zero. And we experience this constantly. Think about a book just resting on a table. It's perfectly balancing the downward pull of gravity with the table's upward push, so the net force is zero. Or, think about being on a bus that suddenly brakes. Your feet stop because of the friction with the floor, right? But your torso's inertia absolutely throws you forward, simply because your body wants to keep cruising at that previous speed. Or, on a much grander scale, picture a stranded ship, engines off, way out in deep space, far from any gravity. It's going to coast at a uniform velocity forever. So, what exactly happens when those forces don't perfectly cancel out? Well, to understand that, we need to talk about momentum. Forget the strict mouth for just a second, and just think of momentum as a measure of an object's unstoppableness. It's that crucial combination of just how massive an object is, multiplied by exactly how fast it's moving. To put that into perspective, look at the difference here. Stopping a heavy, fully loaded truck requires massively more force than stopping a small car, moving at the exact same moderate speed. That makes sense, right? But equally, stopping a tiny, lightweight, but incredibly fast bullet also requires a massive opposing force. The stopping force required is a direct result of that specific combination, mass and speed. And this brilliantly illustrates the real-world impact of how fast that momentum changes. Consider the difference between a seasoned cricketer and a total novice making a fast catch. The seasoned player instinctively pulls their hands backward during the catch. Why? Because it extends the stopping time, which takes the sting entirely out of the impact. The novice, on the other hand, keeps their hands rigidly fixed, stopping that ball almost instantly. Because that change in momentum is so sudden, so abrupt, they experience a massive force. And usually end up with a deeply bruised hand. So the really crucial point here is perfectly summarized in Newton's second law. Force isn't just about making things move. It is the exact mathematical measure of the rate of change of an object's momentum. And actually, that word rate is the key to the whole thing. The harder you want to accelerate something or the faster you want to strip away its momentum, the more force you absolutely must apply. Furthermore, we have to look at what happens at the absolute extremes. When a massive force acts over a tiny fraction of a second, like a batsman fiercely blasting a cricket ball right back down the pitch, we call this specific rapid change in momentum an impulse. It's this incredibly large force delivered in just a split second, producing a finite, measurable, and often massive shift in the body's momentum. Moving on to part 2, the law of pairs, or Newton's third law. Now we really have to ask ourselves, where do these external forces actually come from in the first place? Well, the foundational truth in mechanics is that forces literally never occur alone. Newton famously expressed this by saying, "To every action, there is always an equal and opposite reaction." It's a beautifully crisp phrase, we all know it. But unfortunately, that exact phrasing has birthed a lot of confusing linguistic traps that actually make people totally misunderstand how the physics work. So, to separate myth from reality here, we need a quick reality check on the third law. First off, action and reaction, they're simply physical forces, nothing more mystical than that. Second, there is absolutely no cause and effect time delay. None. They occur at the exact same instant. And third, and honestly this is the most important part, these forces act on entirely different bodies. That is exactly why they don't just magically cancel each other out to zero on a single object. And this means some pretty wild things for our daily reality. Just consider the Earth's invisible mutual pull. When you drop a falling stone, you can clearly see the Earth pulling it downward to the ground. But what you don't see, and I've always thought this is truly mind-blowing, is that the tiny stone is actually exerting the exact equal amount of force, pulling the massive Earth upward. We just don't notice it because the Earth's immense mass means its resulting acceleration is virtually zero. But the force, it's exactly the same. Which brings us to part 3, the ultimate consequence, the conservation of momentum. When you combine the mathematical precision of the second law with those equal and opposite pairs of the third law, it reveals the ultimate balancing act of nature, the conservation of momentum. Think about the physics of firing a gun. The internal explosion pushes the bullet violently forward, but at the exact same instant, the bullet exerts an equal and opposite force pushing the gun backward. That's the recoil. Because they both started completely at rest, the forward momentum gained by the bullet is perfectly negated by the backward recoil momentum of the gun. This guarantees that the total momentum of that isolated bullet gun system never, ever changes from zero. It's the universe keeping perfect balance. So keeping all of these incredible rules in mind, I'm going to leave you with this final puzzle. Imagine you're an astronaut, accidentally separated from your ship in the dead vacuum of deep space, with zero net force acting on you and absolute inertia fully taking over. How do you use these hidden laws of motion to propel yourself back to safety before your oxygen runs out? Think about what you might be holding, think about action and reaction, and think about momentum. Thanks for diving into the